Hi, I'm Charlie Thompson, and I wanted to share with you what I think is the most important, hands down aspect of physical geography, and that's latitude. So I wrote it here because it's important. 95% of everything in physical geography is because of latitude. Latitude is hands down the most important factor in geography. Latitude is the reason that we see the patterns of annual average temperature. So that's the average temperature. You take every day's temperature, add them all together, divide them by days in the year, and you get average daily temperature. That's a function of latitude. The tropics are hot, the poles are cold. That's latitude. Annual temperature range is the difference between the hottest month and the coldest month. That is also a function of latitude. The tropics pretty much have a very, very low temperature range, and the closer towards the poles you get, the higher the temperature range. Latitude also is largely responsible for patterns of rainfall. So let's look at some examples. Here's a whole bunch of maps that I made because I wanted to share this stuff with you. So this is average daily insolation. This is the amount of sunlight coming in per square meter per day. And you can see, well, the tropics in between, this is the equator. This is the Tropic of Cancer. That's the farthest north that you can go and get direct sunlight during the course of a year. This is the Tropic of Capricorn. That's as far south as you can go and get direct sunlight. And you'll notice the tropics, the highest values are at the tropics, not necessarily at the actual equator where you'd expect it to be, but the tropics. The big reason for this is it's usually cloudy over the equator and it's usually clear in the subtropics. We'll spend a lot of time talking about that, but this is insolation at the ground. So clouds over the equator block the sun, but as you'll see, the subtropics, which is where the world's great deserts are, desert, subtropics are the deserts. So as you get away from the subtropics, you can see that latitude is the factor that creates these patterns of insolation. The sunny southwest as opposed to the slightly cloudier east coast, but you can see going from the Tropic of Cancer, as you go north, insolation, energy from the sun just gets, there's less and less and less and less. This is mean temperature, average temperature. So this is all the days added together, divided by the number of days. So there's two factors. The most important is latitude, the tropics. In between the tropics, here we've got, again, the Tropic of Cancer, equator, Tropic of Capricorn. And then on this map, I've got the Arctic Circle. Above that, you have 24 hours of darkness and 24 hours of light. And then the Antarctic Circle, same deal. Below the Antarctic Circle, 24 hours of daylight, 24 hours of darkness. So you can see it's largely a function of latitude, but there's these areas of colder temperatures where it's high. It's cool to be high. So we've got the Tibetan Plateau, we've got the Alps, we've got the Rockies. In fact, let's zoom into North America and you can see the Sierras, this clear area of colder temperatures there. You can see the Appalachian Mountains on the east coast, colder temperatures there. And then finally, the Rockies across Colorado, for example, much colder temperatures there than the same latitude, right? So it's elevation as opposed to just this pattern of latitude across the plain states where it's largely the same elevation. This is temperature range. Again, this is the difference between the hottest and the coldest months. And at the equator, you can see a very low temperature range someplace. These dark blue areas, some of the lowest temperature range is probably 3 to 5 degrees difference between summer and winter. As opposed to moving away from the equator, the temperature range gets higher and higher and higher and higher and higher. Highest range is found in Siberia. 183 degree range between the summer high and the winter cold. It's 183 Fahrenheit degrees. These numbers are Celsius degrees, but you can still see the overall pattern. As you move inland and as you move north, you get higher temperature ranges. Here we've got temperature ranges across the US. You'll notice the effect of water. There's no data over the ocean. I just put a blue tint over the ocean, but you can see as you move north, the temperature range gets higher and higher and higher, going from 8 degrees 8 Celsius degrees, which is like 16 degrees or so, up to 50 degrees difference, 50 Celsius degrees. So 50, yeah, about 100 degrees, just under 90 degrees, 100 degrees, someplace in there, difference between summer and winter. And then the Great Lakes, because they're made of water, and water, it's very hard to change the temperature of water. They have a lower temperature range because they're made of water than the land. But the overall pattern of latitude being the most important factor with temperature range, still very clear. Now we've got rainfall. So I mentioned that the areas right over the equator had lower sunlight values, lower insolation values because of the clouds. Well, you can see it's rainier at the equator, and then right under the tropics, the subtropics, right here, we've got the Sahara and all of Saudi Arabia. We've got the Kalahari, the Namib Desert. And I'm not totally happy with the color scheme that I used for this annual precip. It's very difficult. Not that any of you care about this, but it's very difficult to get to map precipitation. So this is rainfall in millimeters. So 1,000 millimeters are 3 feet. Was it 25 millimeters are an inch? So this is just over 2 inches. The lowest range, this yellowy color, less than 2 inches of rain a year. 125, so that'd be about 5 inches. So this light green color, about 5 inches. You can see most of Australia's desert, 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 and lots of Antarctica, desert, just because it's so cold. We'll also talk about that later. But you can see there's these largely three important regions of rainfall. At the equator, it's rainy as heck. Right under the tropics, it's dry. And then in the mid-latitudes, right where we are, 30 to 50 degrees, it's wet again. So we've got wet, dry, wet, wet, dry, dry, and then wet and wet. So precip, also largely a function of latitude. The other aspect is East Coast versus West Coast. So that would be the other bit. We'll talk about that later. Precip across the United States. You can see the effect of higher elevations. So if it's not latitude, it's plate tectonics. So the two factors in plate tectonics that we're seeing right now, higher elevation is higher rainfall. And the other aspect is off the West Coast, there's a cold current, and off the East Coast, there's a warm current. Because there's a warm current, more water evaporates. So they have more clouds, so they have more rain. Warm current, warm ocean, because it's on the East Coast, that's because of Coriolis force. So precip, again, a function of, for the most part, latitude. 95% of everything in physical geography is because of latitude. The other 5% is plate tectonics. So that's large continents with temperature range. That's places that are high with temperature range and average temperature, and also precip. So again, average annual temperature, you can see the Sierras are cooler. You can see the Appalachian Mountains, the Appalachians are cooler. You can see the Rockies are cooler. So either high latitude or high elevation, both of those are cold. So the reason for this is Earth is spherical. Because Earth is spherical, different latitudes get different amounts of energy on the same day. This creates an imbalance between the equator and the poles. So we'll talk about this. I will talk about this much more in lecture. But at the equator, on this example, the equator is getting direct sunlight, so it's very concentrated. It's hitting the Earth directly. At the poles, though, that same amount of sunlight, that same sun ray, gets spread out over a much larger area. So a sun ray that's that big hitting the equator directly is going to light up that much area, but that same amount of sunlight shining at the poles is going to have to light up a much larger area, so the energy gets spread out. The energy is not as concentrated, so it's cold. The too long didn't read version, the tropics get 2.5 times as much energy as the poles. So there is a constant imbalance of energy with 2.5 times as much energy coming in the tropics as the poles. That sets up weather. So I thought we'd take a look at earth.nullschool.net, and let's go there. All right, so this is the view. If you follow that link, this is the link to earth.nullschool.net. And one of the other things that I wanted to talk about is the winter storm. I'll do that in another video. I just wanted to focus on... Okay, so here is earth.nullschool.net, and let's take a look at temperature as some examples of everything. I'm going to turn off the wind, and I'm going to go to... there you go. So now we're just looking at temperature, and you can see it's latitude going north across the United States, and there's weather patterns. So if we backed it up a couple days, things would look slightly different, but overall, tropics are hot, poles are cold. Places where it's high, for example, here in the Andes, the green areas are cooler than the red areas. That's because it's high. Here we've got the Appalachians, it's high. Here we've got the Sierras, it's high, and the Rockies, it's high. So that's temperature as a function of latitude and elevation. And the other thing I wanted to show you, that's not it. Okay, and this is Google Earth. Hopefully you've had a chance to play with Google Earth. I'll put a link in the lecture slides so you can go and open up Google Earth on your own. But here we've got the same pattern. Here's the tropics, the Tropic of Cancer, the Tropic of Capricorn. And if you look across Africa, this is tropical rainforest right over the equator. And in the subtropics, we've got desert. In the subtropics, we've got desert. In the subtropics, we've got desert. I'm just laughing because Australia looks so different. It is just so very, very, very dry looking. Yeah, that's dry. Here we've got the ITCZ again. So that belt of clouds along the equator, here's the ITCZ. And then in the mid-latitudes, we've got these storms. So this is the storm that we're looking at today, and this storm is coming in shortly. And you can see there's, belt of clouds, all of it rotating counterclockwise around a center of low pressure. Let's look at latitude across the U.S., and you'll see the same pattern. Here in the subtropics, it's dry. As you move north, it gets wetter, well, greener anyway. And it's always fun, the parts of the globe or the parts of the country that you can't see because of clouds, like here, you can't see the Pacific Northwest. If you zoom in, it's green because it's been raining. If you zoom out till you can see the clouds, and you notice you can see the ground, if you zoom in, it's dry. So the parts, when you zoom out, you can see the clouds from the cloud view. It's my experience that the places that you can see, that you can't see through the clouds, those are green. But the places that you can see because they're not clouds, no clouds, you can see those areas because there aren't clouds. But the places that you can see, they're brown because it's a desert. ITCZ, the Intertropical Convergence Zone, subtropical high, polar front. Polar front is rainy. ITCZ is rainy. So that's good for latitude for today. I hope that makes a little bit more sense about why latitude is so important. And it really is just because Earth is spherical, that the equator and the tropics gets 2.5 times as much energy as the poles. So that energy flows from the tropics to the poles, making weather. That's it. I hope you have a good day.